Hello friends, this video is brought to you by www.moeteaching.com.
Let us read the question. Show that every positive even integer is of the form 2q and that every positive odd integer is of the form 2q plus 1, where q is some integer. This question is another application of Euclid's algorithm, and we shall use it to prove the result. Let us first take the Euclid's division algorithm. It says that given positive integer a and b, there exist unique integers q and r satisfying a is equal to bq plus r, where r lies between 0 and b. That means we have to start with positive integers a and b. To prove our result, let us assume that a be a positive integer and b equal to 2. Then, by Euclid's division algorithm, we have a equal to 2q plus r for some q greater than equal to 0 and r lying between 0 and 2. Why? Because we have assumed b equal to 2. Here q is the quotient which will be greater than or equal to 0. R lying between 0 and less than 2 means r can take value 0 or 1. We know that remainder is 0 if the two numbers are completely divisible. For r equal to 0, our a becomes a equal to 2q, and it is completely divisible. A is completely divisible by 2 means a is an even number. So we have proved that if any positive integer is completely divisible by 2, it is of the form 2q. In other words, if a positive integer is of the form 2q, then it is a even integer. Now let us look at the form of a when r equal to 1. A will be a equal to 2q plus 1. That means a can be of the form 2q or it can be of the form 2q plus 1. We have already proved that 2q is the form when a is even number. That implies that if a is of the form 2q plus 1, it has to be odd. We can say a positive integer can be either even or odd. Since a equal to 2q is even form of positive integer, so a equal to 2q plus 1 is the form of odd positive integer. Let us read the question. Show that any positive odd integer is of the form 4q plus 1 or 4q plus 3, where q is some integer. To apply Euclid's division algorithm, let us assume that a is a positive odd integer and let b be equal to 4. Then, by the algorithm, we have a equal to 4 q plus r, where q is greater than equal to 0 and r should lie greater than equal to 0 and less than 4. That means r can take value 0, r can be 1, r can be 2, or r can be 3. And the corresponding form of a will be a equal to 4q. For r equal to 1, a is equal to 4q plus 1. R equal to 2, a equal to 4q plus 2. And for r equal to 3, a equal to 4q plus 3. Here 4q is completely divisible by 2. And we know that any number completely divisible by 2 is even number. So that means a equal to 4q cannot be positive odd integer. Also, since 4q is even, that means 4q plus 2 will also be even, and hence a equal to 4q plus 2 can also not be the odd integer. And we will write, since 4q and 4q plus 2 are both divisible by 2, so these cannot be odd. And we are left with a equal to 4q plus 1 and a equal to 4q plus 3. So a equal to 4q plus 1 and 4q plus 3 are the odd forms of the integer. We will write, therefore, any odd integer is of the form 4q plus 1 or 4q plus 3. A sweet seller has 420 Kaju Barfis and 130 Badam Barfis. She wants to stack them in such a way that each stack has the same number and they take up the least area of the tray. What is the number of that can be placed in each stack for this purpose? Let us first try to understand the question. We have 420 Kaju Barfis. Now 420 Kaju Barfis can be stacked in groups of 2s, which will give us 210 stacks. If we stack them in group of 3s, then we will have 140 stacks. That means more the number of barfis in a stack, less the number of stacks. So let us look at the highest factor of 420. So basically we are finding all the factors of 420. We see that 420 is not completely divisible by 8 and 9. So those are not the factors. Then we can move to 10, which will give us 42 stacks. Similarly, we will have to find factors of 130 and then reach a conclusion, because she wants to stack them in such a way that each stack has the same number. So instead of following this procedure, what we can do is we can find the highest common factor of 420 and 130. HCF will give us the number of barfis to be put in each stack such that each stack has the same number of barfis and they take up the least area of the tray, that is, the number of stacks of barfis are minimum. So let us find the HCF of 420 and 130 by Euclid's algorithm. we have 420 equal to 130 into 3 plus 30. Remainder is not 0, so we proceed with 130 equal to 30 into 4 plus 10. Again remainder is not 0, so we proceed. We take 30 equal to 10 into 3 plus 0. This gives us that HCF of 420 and 130 is 10. This means that the sweet seller can stack each variety of Barfi in stacks of 10, and in that way the Barfis will occupy the minimum space and each stack will have 10 Barfis. Just for the explanation's sake, let us understand, if we had taken the factors of 130 also, then the common factors of 420 and 130 would be 2, 5 and 10. Out of these, if we would have stacked them in 2 Barfis each, how many stacks we would have had? 210 plus 65 stacks of Barfis. That would occupy more space. Similarly, if we had stacked them in groups of 5, then also we had 84 plus 26 stacks. But when we stack them in groups of 10s, that means each stack has 10 Barfis, the area occupied will be minimum because number of stacks is 42 plus 13. That is the minimum number of stacks.